Bonjour and welcome back to another episode of T.E.D Mini, where together we'll be learning about technology, engineering and design. In today's episode we'll be learning about circuit basic principles and Ohm's Law. Before we get into Ohm's Law, let's understand some basic principles. In science, we say that everything is made up of atoms. Atoms are tiny particles that are so small that we cannot even see them with a microscope. Atoms are actually made up of three smaller things: a positive charge, a neutral charge, and a negative charge. A number of positive and neutral charge cuddle together in the middle of the atom, while the negative charge floats around the outside like planet around our sun. The positive charge are called protons, and the neutral charge are called neutrons, and the negative charge are called electrons. Depending on the number of protons, neutrons and electrons that are inside the atom, we have different material. Some materials have electrons which are not stuck to an atom and are free to move around. These free electrons are very useful as they can carry charge from one place to the next. Metal wires are a good example of this. Now let's think of these wires as part of a simple circuit. Let's imagine that these free electrons inside our metal wires to be lazy mice inside a corridor. A battery cell, on the other hand, is like a person who is pushing the mice forward through the corridor one by one. However, the battery will only push the mice forward if both ends of the corridor are connected to each end of the battery. A lamp is like a revolving door in a hotel, which is a bit of an obstacle in the middle of a corridor. The bigger it is, the harder it will be for the mice to push it round to go through. Now, let's talk about Ohm's Law. Ohm's Law is an equation which helps us understand the relationship between the three most important components in a circuit, which are voltage, current, and resistance. Voltage, or just a capital V for short, is the size of the muscle of the person inside the battery cell. This strength is measured in volts, its symbol being V. A battery cell has a fixed voltage of 1.5 volts, meaning all the persons inside the battery cell will all have the same amount of muscles. To make the mice move through the corridor faster, we can add more battery cells together. This will increase the voltage of the battery as now more persons will be pushing the mice along. The speed with which the mice are traveling through the corridors is called the current, or just a capital I for short. Current is measured in amperes or amps for short, its symbol being A. And finally, we said that the bigger the revolving door is, the harder the mice will have to push the door to pass through, thus slowing them down. This slowing down force is called the resistance. Resistance, or capital R for short, is measured in ohms. Its symbol is the last letter of the Greek alphabet, which is called omega. Now, let's take into consideration a simple circuit with just a battery cell of 1.5 volts, some wires, and a lamp which can take a maximum of 4 volts. To measure the current in the circuit, we will add an ammeter, which is like a speedometer for the mice. Remember, the wire going around the circuit is the corridor filled with lazy mice. The battery is the small room with a person pushing the mice forward one by one, and finally the lamp is the revolving door which is slowing down our mice. When the circuit is connected, the ammeter measures a current of 0.1 amperes passing through the circuit and the lamp is only lighting up just a little. To make the lamp light up brighter, we need to add another battery cell. Now, the voltage across the battery is of 3 volts. The ammeter is measuring 0.2 amperes, which is double, and the lamp is lighting up much more brightly than before. If we had to add another battery to the circuit, we'll now have a battery voltage of 4.5 volts. However, this time round, something very strange will happen. The ammeter will initially read a current of 0.3 amperes, then drop to 0 amperes. The bulb will also light up very brightly at the same time and then burn out. This is because the amount of voltage trying to pass through the bulb is higher than its maximum voltage of 4 volts. To make the bulb light up at its brightest, we could use the 4.5 volt battery and add a fixed resistors in series with the bulb to drop the voltage going through the bulb to 4 volts. But we still have one big problem. To calculate the size of this resistor, we first need to calculate how much resistance is being made by the light bulb. To calculate the resistance, we can use a very simple equation called Ohm's Law. The equation is very simple. Ohm's law states that the muscles that are needed to push the mice through the revolving door is equal to the speed of the mice multiplied by the amount of resistance that is being made by the revolving door. Or in proper terms, the voltage drop across the lamp is equal to the current in the circuit multiplied by the resistance being made by the lamp in this case. To find the resistance, we need to change the subject of the formula of the equation. To do this, we can use a very simple trick. Draw a triangle and divide it into three as shown here. At the top write the voltage, and in the bottom sections we will write the symbols for current and resistance. The voltage and the current are on top of each other, so we will write a division sign in between the two. The voltage and resistance are also on top of each other, so we will also write the division sign in between them. However, as the current and the resistance are next to each other, we will write the multiplication sign in between them. Now, to do a quick subject of the formula, we can do this. If we want to find the voltage being dropped by the lamp, we cover V, and we are left with the current multiplied by resistance, as we have said before. If we want to find the current in the circuit, we cover I, and we are left with the voltage divided by the resistance. If we want to find the resistance in the circuit, we cover R, and we are left with the voltage being divided by the current in the circuit. As in our case we need to find the resistance, we'll use the equation R equals V divided by I. Taking into consideration our first circuit, we do not know the resistance, so we'll write it down again. We then know the voltage dropped by the lamp as being 1.5 volts, and the current in the circuit as being 0.1 amperes. So if we divide the two, we'll have the resistance of the lamp. If we do the same for the second circuit, we know the voltage being dropped by the lamp to be 3 volts now, and the current to be 0.2 amperes. If we again divide the two, we will again be able to work out the resistance of the lamp. As you can see, although the voltage and the current are changing, the resistance of the lamp always remains the same. As to our third circuit, we cannot work out the resistance as the battery voltage was too high and burnt out our lamp. This happens because our battery is now 4.5 volt, and our lamp can only take a maximum of 4 volts, so it got burnt. The solution is to stop the extra battery voltage from passing through the lamp using a fixed resistor. But what size of resistor do we need? We can calculate the size of the resistance by using Ohm's law. But as the current in a circuit changes each time we add a resistance, we first need to find out the amount of current that will be passing through the circuit when the voltage is 4 volts. If the voltage across the lamp was 4 volts, and we know the resistance of the lamp to be 15 ohms, we can divide the voltage by the resistance to find that the current that will be passing through the circuit will be 0.27 amperes. Now that we have the current, we can find the amount of voltage that we need to stop. We do this by subtracting the voltage of the lamp from the voltage of the battery. That is our voltage drop of 0.5 volts. Since we have both the voltage drop and the current, we can divide the voltage by the current to find the size of the resistance that we need, which will be 1.85 ohms. And that will be all for today's episode of T.E.D. If you have been, thanks for watching.